Welcome back. So now that we understand how the order of the orbitals sets up, so that which orbitals fill first and so forth, and how we can use the periodic table to lay out this order for us, let's actually look at some elements and place the electrons in them. Now, doing this is what's called the electron configuration. So the electron configuration is just a symbolic way to represent where the electrons of a given element are. So what orbitals they exist in. And we'll go through how to write this out in just a second. Now, I've told you that there's many ways to remember this order. So you could simply memorize the order. Right? You can use the periodic table to trace the order. Now, you can also use a diagram like this, which lays out the order of filling in a sort of diagram sense. So the way this is done is that we put all of the s orbitals, right, in the first column. So we have the 1s, 2s, 3s, etc. And in the next column, we place all the p orbitals lining up the numbers for the energy level. So since the first p is at 2, we go from 2p to 7p. Then we do the same thing for the d's, starting at 3d, and so forth. And then the f's, etc. And then in terms of filling, we simply draw lines starting at the upper right and going down and to the left. So we would start up here and we would fill the 1s. And then we go back up to the next diagonal and we fill the 2s. And then we go back up and we fill the 2p and the 3s. And then we go back and we fill the 3p. Now, this is where, either using the periodic table or this kind of chart can be helpful, is that it automatically, after the 3p, takes us to the 4s, right, and not the 3d. Right? So we go to the 4s, then we go to the 3d, the 4p, and the 5s, and we just keep going until we use up all the electrons. And so this is yet another way to sort of organize how you remember the order. So there isn't any one of these that's perfect. It's sort of what's going to work the best for you. Now let's get down to the business of actually writing this. So there are two different ways that we can write it out. We can write out what's called the complete electron configuration. So for example, right, if we're looking at nitrogen, nitrogen is element number 7, so atomic number 7. So it's going to have 7 electrons. And its electron configuration would look something like this. All right, we have 1s2. So the superscript here tells me how many electrons are in this set of orbitals. So we got 1s2, right? And there can only be 2 because there's one orbital, hold 2 electrons. The next one is 2s, 2. And then we have 2p. And notice there's 3 here because there's only 3 electrons left, right? We had 2, 4, 7. So if you add up all the superscripts here, they're going to add up to the total number of electrons. And if you see, you move down to oxygen, you have 8, and fluorine 9, you can see that each time we just add 1 into, in this case, the 2p. We go 2p4, then 2p5, and at neon, we fill up that 2p and we get to 6. So notice a p is going to max out at 6. And as we can see from up here, a d is going to max out at 10. And an f is going to max out at 14. Right? Because remember, we have sets of orbitals and every orbital can occupy 2. So if a d set has 3 orbitals, each can have 2, that's 6. A d set has 5 orbitals, 2 of them means 10 electrons, and f is 7 orbitals, so a total of 14 electrons. Now, there's also what's called the noble gas configuration. So this is really a shortcut where we use the noble gas to represent a block of electrons. And so we'll get to this in a second and we'll do an example. Now, an alternative way to do this, besides an electron configuration, is what we call an orbital diagram. And this is a more descriptive way to show the electrons using arrows. So if we look over here, we can see the orbital diagram that would go along with these electron configurations. So for nitrogen, we have our electron configuration. If we wanted to lay this out in an orbital diagram, we would draw little boxes for our orbitals. So our 1s, we have one box, right? We have 2 electrons. Notice we use a half arrow for each electron. And notice they're pointing in opposite directions, and we'll talk about why that is a little bit later. And we go to 2s, right? It has 2 electrons, 1 up, 1 down. Now notice we go to 2p. We have 3 of them. So we have 1 electron in each. And this is going to be a theme of how we fill these sets of orbitals, whether they're p orbitals or d orbitals. Anytime we have more than 1, we always put 1 into each before we start to pair them up. So if we move down to oxygen, we see since we have 4, we have to go 1, 2, 3, and the 4th one fills up the first of the p orbitals. And then if we have 5, we fill up the second one, and you get to neon, and you notice now you've reached the end and filled up that 2p set of orbitals with the 6 electrons. So orbital diagrams. Now, why are the noble gases sort of special? Well, notice noble gases, right, are group 8, right? That means they have 8 what we'll call valence electrons. And again, we'll talk about some of these terms a little bit later in more detail. But more importantly, that means they have a filled S and P orbital set for a given energy level. So for neon, that's the second level, has a filled S and a filled P. And so because these are filled, we can use them to represent this block of electrons, or in other words, to represent these 10 electrons. And that's what we're going to use when we do the noble gas configuration. So let's draw this out, and we'll do chlorine as an example. So if we look at the periodic table, right, chlorine is element 17. So it's going to have 17 electrons. And we can write this out, right? So if we either follow along on the periodic table or follow along with our chart, right, we're going to fill up the 1s, 2, then we're going to go to the 2s, and we're going to have 2. Next we go to the 2p, we have 6. Now, we've used 10, we still have 7 more to go, so after the 2p, right, we go to the 3s, and we fill up those 2. After the 3s comes the 3p. We have 5 electrons left, and those 5 electrons will go into the 3p. So we end up with 1s2, 2s2, 2p6, 3s2, 3p5 for our 17 electrons. Now, noble gas configuration. So if you look at chlorine, going backwards, the nearest noble gas is neon, right? And neon has 10 electrons, right? So what neon can do is represent this block of 10 electrons. And the way we do that is we just simply write neon, we put it in brackets, and that's representing that filled S and P of the second energy level. And then we write the remaining configuration. So it's really just kind of a shortcut, which can become, a little bit easier when you get to bigger atoms that have more and more electrons. Now, what about the orbital diagram? Now, I'm just going to do the orbital diagram for these last ones. I'm not going to worry about doing these that are filled, right? We could draw them out, but to save us some time, I'm just going to do the 3s and the 3p. So the 3s, there's 2. In the 3p, we have 5. So we've got 1, 2, 3, 4, 5. And so we got the first 2 of these are filled, and we have one more electron that could go in there to give us our 6th electron in the 3p. So this would be our orbital diagram for the chlorine. So I could just write neon here if I just wanted to make sure that represent. But drawing out the orbital diagrams, typically we only draw them for the last, or what comes after the noble gas in the noble gas configuration. Okay, so now we've got to start here. Let's do some more. So we're going to put this diagram up here because this is the way that I prefer thinking about it, is using the periodic table, because again, we always have access to the periodic table. And we're just going to run through some examples. And I'm going to do the electron configuration and some of the orbital diagrams here. So first thing, we're going to do rubidium. Rubidium is in group 1, right? It's element 37, so that's 37 electrons. Now, if you go back, the noble gas that we could use, right, and this is where this becomes useful, is going to be krypton. Right? And krypton has 36 electrons, right? And then, right, and so that's going to be at the end of the 4p right here. And rubidium, we go into the 5s1. You do the orbital diagram, right? We would just do the orbital diagram for the 5s, and it would look like that. So let's do Si. So Si is element 14. So again, this one we can just write out, or we could use neon with its 10 electrons, and then just go from there. So after neon, we're going to go 3s2, 3p2. And so if I was writing out my little diagram, I would have my 3s, my 3p, I have 2 here, 1 here, 1 there, to give me my orbital diagram. We do the next one, I. Again, this is a pretty big element. I is up there around 53, right? Element 53. So again, krypton is the nearest noble gas. That'll represent the first 36. And then we got 5s2. Right? And then after 5s comes 4d. Now that can have 10. So now we're at 48. And then we go to 5d, and we can have 5d5. Right? And so that's the 53 electrons of iodine. Now, begin to write out the orbital diagram. Typically we would just, 5p. We would just write out the s and the p orbitals. So we would write out the 5s and the 5p, and again 1, 2, 3, 4, 5. And we can keep going with these. So Fe, right? That's element 26. So we can use argon with its 18 electrons. and then we're going to go to 4s2, and then 3d, and we have to go over 5 spots in the 3d, right? Because we have 18, 20, 6 spots. So we got our 26 electrons for iron here. And again, our orbital diagram. Here, since the D is only partially full, we're going to write it out. And so have my 4s, and I have my 5 orbitals of my 3D. I have 1, 2, 3, 4, 5, 6. And then we got zinc. Zinc is element 30. And again, you're going to have argon, 4s2, that's 20, 3d, 10, right? Zinc is right here, right at the end of the, we filled up that 3d. And again, I'm going to skip the orbital diagram here. I think we get the idea of how we would draw those out. Now, the last 2 examples here are ions. So just like we can do electron configurations of atoms, we can do electron configurations of ions. So zinc 2+, the 2+ charge means we've lost 2 electrons. So whereas normal zinc has 30 electrons, zinc 2+ is only going to have 28. So if I look at what zinc was, right, 4s2 3d10, I'm going to lose 2 electrons. Now, the important thing is that the electrons are going to go out of the highest energy level. Now, you might think you want to pull these out of 3D because they were the last to fill. But one thing to note is that anytime you're working with these transition elements, right, you're always going to lose these s electrons first. And so it's just one thing, it's just one of the things we have to remember, that we're always going to pull those s electrons out first. So we got argon, we're going to lose the 2 4s electrons. So you could just omit it, or you could even write 4s0 just to make and emphasize that. 3d10. And so this would be our 28 electrons. So we've lost those 4s electrons to give us the 2+ charge. Now O2 minus. So oxygen is element 8. And so with the 2- charge, has 2 extra electrons, has 10. So I'm just going to go ahead and write out the full. So this is 1s2, 2s2, and oxygen would normally be here, right? We gain 2, and we get over to be like neon, or in other words, we have 2p6, right? So remember, these main group elements are going to gain and lose electrons to become like noble gases, right? So this is the same thing as neon. Now, we shouldn't write that out by just drawing the noble gas, right? We should only use this noble gas to represent part of an electron configuration, but we want to understand that a lot of times these ions of these main group elements are going to have the same electron configurations as a noble gas. All right, so those are a little bit of practice, and you know, the more you do this, the easier it is. But again, if you follow along, follow the order, either using the periodic table or using one of those graphical tables that we showed, it's just a matter of filling up the orbitals as you go. Now, let's look at some of the rules that we've mentioned along the way and summarize them. So there's 3 big rules that we follow when we fill these orbitals. The first one is sort of the big general rule. It's called the off-bow principle. And this means that the orbitals fill starting at the lowest energy and just progressing up to the higher energy. So we always start at the 1s because that's the lowest, and we always go in energy order. And we fill up the block, the set of orbitals, and then we move on to the next set of orbitals. As we're filling them, we're going to follow what's called the Pauli exclusion principle. And this essentially means that we can have two electrons in any orbital. So what this really says is that no two electrons in an atom may have the same set of 4 quantum numbers. And we'll talk in the next section about what exactly we mean by these quantum numbers. But in practical sense, what it means is that we can't put any more than 2 electrons in an orbital. And these electrons are going to be pointing in the opposite direction, or as we'll see in a little bit, they have what we call opposite spin. So only 2 electrons per orbital. And when we fill sets of orbitals, so when we fill a p set or a d set, we follow what's called Hund's rule, which is when we fill them, we always place 1 electron in each orbital before we pair them up. So as we went through that, we did the orbital diagrams. We always put 1 electron in each of the orbitals of the p set or the d set before we started doubling up. And that's called Hund's rule. So we followed these basic rules. We followed the order. We'll come up with the orbital, the electron configuration, or the orbital diagram of any element on the periodic table. Now, I'm not going to lie, there are exceptions of the few elements, and you can see these listed on some of these. But, the only way to really know these is by experimentation. So if I'm asking you to do this, I'm going to ask you to follow the basic rules. And there's really no point in memorizing a lot of exceptions, right?